Alright, AP Physics 1, this is going to be the final video on the simple harmonic motion unit, and in it we're going to talk about the other type of simple harmonic motion system we want to be familiar with, that of a pendulum. So first, let's make sure we understand what a pendulum is. So we have a ball, some sort of mass here, hanging from a string, and we're going to offset this a little bit, and then when we let go, it's going to swing back and forth until it returns to its original position. And that would be one cycle, and these cycles would keep going and going. And this is what we define as specifically a simple pendulum, meaning that there's nothing more complicated happening here, there's nothing else hanging, there's no joints in the string or anything like that. And there's a few terms we need to know. First off, the mass on the end, which we're going to say has some mass m, is known as a pendulum bob. That is actually the word for it. I didn't just give it a name. You can kind of think of it because it's bobbing up and down as it moves back and forth. It is hanging from a string of length L. I wrote it with a cursive L here so we can make sure it doesn't look like a 1. And this is we'll say a massless string or rod, and by that we just mean it has a lot less mass than the bob itself. So all the mass is concentrated at the end, not throughout. We've displaced it by some angle theta, and it's going to swing to that angle theta on the opposite side. And additionally, we call this position at the bottom the equilibrium position. Now, is this pendulum going to be moving in simple harmonic motion, though? Well, remember, what is the defining characteristic of simple harmonic motion? The displacement of the mass, which in this case is the pendulum bob, must be directly proportional to the restoring force on this bob, the force that pulls it back to equilibrium, and also opposite in sign to that restoring force. So let's look at these pieces individually, the displacement and the restoring force. And let's start with the displacement. And the displacement is going to be basically, so if this pendulum was to go in a complete circle, it would make a circular arc, and we would have something here that we think of as like the arc length. So it would actually be a little bit curved, but if we're close enough, this will be a fairly straight line. This will be our delta x. And the equation for an arc length is equal to basically the distance from that pivot point, the distance from the center of the circle, so that would be L, times the angle it has moved through, theta. So the displacement here would be delta x is equal to L times theta. Now, one quick note, typically speaking, we don't call the displacement the amplitude for a pendulum. We usually call the angle the amplitude, and that is largely because the angle and the displacement are basically directly proportional to each other. So if we increase the angle, the displacement increases a set amount just based on the length of the pendulum. And then the other piece we need to look at is the restoring force. Well, let's talk about the forces in general. Well, the forces, when it's at equilibrium, are balanced, and what are those forces? Fg, the force of gravity, or its weight, going down, and the tension force going up, and those are balanced. And if we offset this a little bit, well, we've got the force due to gravity still down, and the force of tension is still towards the center. But the thing is, though, is that they're no longer balanced. So what exactly is the direction of the net force? So if I wanted to figure that out, I could add these vectors tip to tail. So I'm going to actually take my Fg vector and I'm just going to shift it up a little bit until it is on the tip of the tension vector. And notice this will still be some angle theta here because this one's going straight down. This is going with the angle of the string. So this theta matches this theta. And if we were to find the net force then, well, it would just go from this point down this way. And that makes sense. This net force is pointing back towards the equilibrium position, so it would in fact be our restoring force because it is pointed away or in the opposite direction of the displacement. We've pulled it to the right, the restoring force pulls to the left. We pull it to the left, the restoring force pulls back to the right. But what is the magnitude of this restoring force? Well, keep in mind that I have basically right here a right triangle. These are perpendicular to each other, and I have theta, so this piece here would be equal to the hypotenuse of this triangle times sine of theta, or the restoring force is therefore equal to Fg sine theta, or if I want to substitute in for the weight, mg sine theta. But there's an issue here. For this to display simple harmonic motion, the displacement and the restoring force, well, they have to be proportional to each other. But these aren't exactly proportional anymore, right? Because if we look, this is proportional to theta, and this is proportional to the sine of theta. And those aren't the same thing. So what exactly can we do here? So once again, we have these two equations. Delta x is equal to L theta, that's the displacement, and the restoring force of the net force is mg sine theta, and as of right now, they are not directly proportional to each other, so the pendulum would not be displaying simple harmonic motion. But let's take just a second, and let's go ahead and quickly, I'm just going to graph here a graph of sine theta. So this is just y equals sine theta, where theta is in radians, and we see we get this nice sinusoidal pattern here. But let me go ahead and put on top of this a graph of just y equals theta. Now keep in mind, since theta is on the x-axis here, this would be equivalent to a graph of y equals x. So it's just going to be a straight line. So the red line is y equals sine theta. The blue line is just y equals theta. So it's just going straight up and down in that diagonal. And if we look here, we notice something very interesting, which is if we look in this region, right about here, so this is about 0.4 radians in each direction past 0, we notice that the two curves are essentially identical. And in fact, this is a very, very useful thing because we are going to now kind of use a little mathematical trick that will make our life a lot easier. And this is actually very, very common in physics in general, what I'm about to do. And this is something known as the small angle approximation. And what that tells me is that if theta is smaller than about 0.4 radians, which is approximately 20 degrees, so if theta is smaller than that, theta and sine theta really equal the same thing. So I'm just going to really specifically say, all right, let's say we confine theta to being less than 20 degrees. Well, if that's the case, this is just going to become theta, and the net force now becomes mg theta. And now these are directly proportional to each other, the displacement and the restoring force. So I've once again gone ahead and just basically put up this drawing, but now I'm going to put a really, really important caveat right here, which is that a simple pendulum will only display simple harmonic motion if theta, that angle, is less than about 20 degrees. So we want to be very, very careful. We're not going to be looking at situations greater than 20 degrees because then everything we're about to analyze, it starts to become way more complicated because it's no longer specifically simple harmonic motion. It becomes a slightly more complicated situation. Now let's talk about a couple things here. Let's say we want to analyze the period of basically this swaying back and forth, this bob going both directions. So how long it's going to take per cycle. Well, what factors affect this period, that amount of time, which I'm going to abbreviate TP for just the period of a pendulum? Well, the first things first is that if we have a bob with more mass, well, if it has more mass, it's going to have more inertia. It's going to resist the acceleration more, so that's going to increase the period because it's going to cause it to go slower. Next thing, if we displace it more, if we pull it to a greater displacement, well, it's going to take more time because it's got more distance to cover, so that's going to cause the period to go up. So once again, it's going to make it slower. And lastly, well, if we can make the restoring force bigger, that will make the period smaller, because if the restoring force is bigger, it's going to get pulled back faster. It's going to be accelerated more heavily, and that's going to once again cause it to go faster. So let's try to assemble all these pieces into an equation. And once again, I'm going to kind of cut a little bit of a corner here, and I'm going to go ahead and tell us that the period of a pendulum is equal to 2 pi, the square root of something. It's very similar to the mass spring equation, and we're not going to go through a full proof here, so you're going to have to take me on my word a little bit. So we've got TP is equal to 2 pi, the square root, but what are the different factors we said? Well, one, we said if the mass goes up, the period's going to go up, so those are going to be directly proportional. We have if the displacement goes up, the period goes up, and we have if the restoring force goes up, the period goes down. So that's going to be underneath here. That's going to be inversely proportional. So we have this equation here, and let's go ahead and start substituting in those equations we had for delta x and for the net force. So I'm going to say TP is equal to 2 pi, the square root of m L theta over mg theta. And remember, this was only the case if theta was less than 20 degrees. So we have to make sure we keep that in mind. But if I look at this now, I have a lot of things cancel out. The masses cancel out, and the thetas cancel out. So I am left with Tp, the period of the pendulum in seconds, is equal to 2 pi the square root of L over g, where L is the length of that pendulum in meters, and g is the acceleration due to gravity, at which on Earth is 10 meters per second squared. Now keep in mind, if you had this pendulum on a different planet or somewhere where g is different, we would have to have a different value there. And something important to notice here is just because we cancel these out in the equation, the mass does not affect this period of the pendulum, because increasing the mass increases its inertia, but it also increases the force it's being pulled with. And also the angle does not affect the period, because if we increase the angle, it has more distance to cover, but once again that also increases the force being pulled on it. But remember, although the angle does not affect the period, that is only true up to about 20 degrees. If we get greater than 20 degrees, we can no longer make that assumption. So as long as we stay in that area, this equation will be sound. Lastly, let's take a second and just look at the energy of this pendulum system, though specifically it would really be the pendulum and the Earth, and we'll see why that is in a second. And most of you could probably do this analysis pretty much completely on your own, but we're still going to go through it just for completion's sake. So we have our pendulum here, we've offset, and it's going to swing down to equilibrium. And when it's at equilibrium, what are the energies that it has at equilibrium, that this pendulum Earth system has? Okay, well, it's going to be moving, so it's going to have some kinetic energy, and it's above the ground, so there's some gravitational potential energy. But to make our life simple, let's go ahead and say that the lowermost point of the pendulum we're going to define as y equals 0. Because when we do that, we can eliminate the gravitational potential energy. We're not looking at any point below this, and therefore all of the energy at the equilibrium point will be kinetic as long as we define our system in this way. The pendulum is then going to swing upward to the other side, to its other, maximum position. And when it does this, it's going to briefly stop. And when it stops for that instant, the velocity goes to 0, the kinetic energy goes to 0. So the only energy it's going to have here is gravitational potential energy. So once again, we have a system where the energies are flipping back and forth between kinetic and gravitational potential, because these are going to end up being the same value. The energy of this whole system is in fact going to be conserved. So then when it swings back down to equilibrium, it all becomes kinetic again, and when it swings up to the other side, it is now all gravitational potential. And if we were to look at some position between the two, like there for instance, it would be some combination of the energies. Now, one last point to make is just looking at the equations. That means the equation for the energy at the bottommost point, it's all kinetic, so that would just be 1/2 mv squared. And at its two top points, the energy is all gravitational potential, so that would just be mgy. And keeping in mind that that y is the distance specifically between basically our bottommost position and the topmost position. So it's just the vertical displacement. We don't care about the horizontal at all, just the vertical displacement there. That will be y. So that's it. That concludes our unit on simple harmonic motion with this lesson on pendulums. So at this point, can we determine if a pendulum will display simple harmonic motion given the particular parameters of a situation, keeping in mind that theta, that angle of displacement, needs to stay less than 20 degrees. Can we calculate the period of a pendulum using T sub p is equal to 2 pi the square root of L over g? And can we analyze the energies of a pendulum and use the conservation of energy to determine specifics of its motion? Because we can figure out, for instance, how fast it's moving at the bottom, how high it's gone up, and things of that nature, keeping in mind that at the bottom, all of the energy will define as kinetic, and at its two top points, all the energy will define as gravitational potential energy.